Okay. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum rahmatullahi wa barakatuh. Hello, everybody, and welcome to a new webinar on deep learning for computer vision. This webinar is part of our internal summer training program for the student of computer engineering at KFUPM. And we have a special guest tonight. We have with us Dr. Ibraheem Hashem, who insisted that he will introduce himself. So I'm not going to introduce him, so I will leave that for him. But I would like to mention a few things about our relationship with Dr. Ibraheem. Dr. Ibraheem is helping us in the training course, and he's also hosting two of our students for the summer training. So on behalf of the chairman of the computer engineering department, the faculty, and the student, I really want to thank you, Dr. Ibraheem, for all the things that you are doing for us. Thank you.
Thank you. All right, so I start now?
Yes.
Okay. All right. Thank you, everyone, for thanks, Dr. Yahya, and for the whole department for this opportunity to be talking today about practical deep learning for computer vision. My name is Dr. Ibraheem Hashem. I work with the Visual Computing Center at KAUST. Most of our research is related to computer vision and graphics. So, all right. Yeah, as Dr. Yahya said, I'll just give you a quick kind of a summary or timeline of my academic journey, and maybe this is something that you can look into or think about. Okay, how did someone get a PhD in this field, in this area? So I actually started off as a KFUPM student. I was going to study software engineering, and there was a wave of scholarships, and I applied. I ended up in Portland State University in Oregon. I took my Bachelor of Science in Computer Science. And after that, I moved on to Simon Fraser University in Canada to study for my master's. And I got it in 2011. And the main driving factor for this was the lab there was studying computer graphics. And that's the area that I really love. And I continued on with the same group, and I got my PhD in 2016. And when I came back, I got invited to give a talk at KAUST, and I discussed with them, and then there was an opportunity for a postdoc at KAUST. And this is in 2017. Now I'm back to the East Coast, or the MUM, and what I'm doing right now is I'm doing a remote researcher. So it's an extension of what I was doing at the postdoc at KAUST. And I also have my startup where I'm the lead technical person there. And we work on different projects for digital transformation or artificial intelligence. I also consult for a large research group in Riyadh, which is just starting up, and we're actually hiring. So if someone is interested in computer vision and research and AI, please reach out to me. So this is enough about me. Let's start to talk about deep learning. So on the agenda today, we're going to discuss the basics of machine learning and deep learning. I'll mention the architectures there are, some talk about frameworks, and showcase some of the latest advances in the field. We're also going to do a simple short tutorial about building an object recognition application from start to end. So this is a hands-on part of the talk. And I'll end up with some kind of notes and comments about applying deep learning to your work. So this deep learning approach to machine learning have gained a lot of traction. And one of the highlights in the last couple of years is this AlphaGo self-teaching model that was able to be the top Go player. And this is something that used to be thought of as a very difficult problem. It's a very difficult game with lots of branching and decision making, and computers were able to beat the top player in the world, human player. Um, we've seen also work in uh, human-like speech synthesis from text. So Google right now has one of the top models, and when it comes to translating text into human-sounding voice. There's also models from Stanford University that were able to classify skin cancer by looking at pictures at a high level and at competitively to specialists in the field. There's also things that are kind of very interesting artistically. We have this unpaired image-to-image translation. In this case, you show the model pictures of horses and pictures of zebras, and then you ask it to translate from one to the other, and you get these kind of artistic results that are kind of remarkable, and it's very difficult to actually try to draw them as an artist. There's also um, an increase in the ability of models to be able to tell you a lot about a picture. So you give it a picture, and it will tell you maybe these people are snowboarding and they're wearing jackets. So you give it a picture, and it actually gives you a description of the picture. It's not just there's a dog here, but the dog is eating X and he's sitting on Y, and so on. There's also works about object detection. So in a given scene, you can find what are the objects, the cars, the people, and maybe subcategories of buses and so on. This is very useful for the systems that do autonomous driving. So let's go back one step. Machine learning can be roughly divided into these three uh, classes of learning. You have your unsupervised learning, which generally is about dimensionality reduction. You want to do big data visualization. It's also about clustering. So maybe you want to find out who are your customers or put them in clusters, and that will help you in your marketing strategy. There's also supervised learning, which is the sort of easier way of learning. And what you do is you provide a model with the answer and a lot of examples with the answer, and the model will learn um, things like classification. So what we saw before, you see a scene and then you can find, okay, this is a car, or this is a human moving. There's other things that are also important, like identity fraud detection. So you give it a list of transactions from a bank, and it will try to identify something that looks fishy. And things like regression, maybe you could do some weather forecasting, and hopefully maybe market forecasting for better planning. There's also a branch for reinforcement learning, so relatively new, or it's still not mature yet, but it's gaining a lot of interest in the areas of robotics and navigation, and in general agent AI. So there's an agent in an environment, and how can he react? And on the right here, I show this conceptual figure. So this is not a real thing. It's just a conceptual idea about machine learning. So if you assume that the human is, in terms of level of intelligence or level of ability in all of these tasks that I talked about on the left, is at this point, then the assumption here is that once you feed these models, these machine learning models, more data, you are possibly going to end up with a point where the model might um, uh, surpass an average human performance. So in the case of like I said, a Go, then it's had enough time to train and learn from its mistakes, and it was able to beat a high level human in the area or in that field. Now we have two lines here. One is this traditional machine learning, where the progress was steadily picking up, And we have these deep learning, big neural network models that seem to be much faster. Once you give it enough data, it, it learns much faster and be more performant than these so-called traditional machine learning. Now, this is not the real world. This is not a real figure of some performance, but this is the sort of the concept is, okay, if I have a lot of data and I have the right neural network, then I'm able to perform these maybe superhuman capabilities in terms of accuracy or speed. So generally, when you're a computer scientist, you're a programmer, you are most commonly working with this sort of imperative programming. So you have inputs, so a picture or a number or whatever, and you have an output, and your program is written into these series of commands to perform some algorithm that gives you an output. For example, this is an exact solution for the greatest common divisor, and if you run this with, you know, X amount of a million times with any number, you will always get these kind of almost perfect solutions. So if you have a problem that has a closed form solution, something that you can solve it with these branching and loops, then imperative programming is the real way. It's always, almost always the best way to go about things. So you have an input, you have an algorithm, you have an output. Now, if you try to think about problems that are more complicated, not something that you can describe in a mathematical function or an algorithm, then what traditional machine learning used to do is have the same, some input is, and of course here the problem would be something more complex than just finding a number. It would be maybe finding a face in a picture. If there's a picture and you want to find the human face. So you got an input, and then what you do is you do these feature extraction process. Most of the time, these would be handcrafted, or it would take a lot of skill to build these feature extractors. You take the input, you apply a feature extractor, you get some kind of representation of the same input, but it's a rich representation. Then you could apply some machine learning algorithm like cluster things, and you get your outputs. And you can say, all right, there's a face here based on that. The problem that, like we said, the feature extraction here is very difficult, and you have to be someone within the field, and you have to maybe have some kind of hard-coded rules about extracting the best features. This is where deep learning to me seems to shine, is you have this end-to-end system. So what you have is an input and you have a output, and inside here you have this hands-off process of letting the model, letting the learning process learn how to do this feature extraction and inference on, okay, what the output is given this new input. So what are the inputs? Generally in machine learning, you have things that are usually, you want something that's useful for your day-to-day life, or you have a robot, or you have whatever kind of application. So you feed it images, so it deals with something visual. You give it audio, you want it to generate a sound, or it wants to understand when a human is talking, or videos, which are just a series of pictures, or 3D volumes. So these are the type of inputs. And in all of these, we take them from the natural world and we digitize them into generally pixels for images and some amplitude for audio. And the same for the videos and 3D. So it's going to be a set of numbers, a large set of numbers, and that's how you describe an input in the natural world. It can also be observations about the natural world. So in this case, a day of the week is sort of a human construct, or a day in the year. There's some relation to the natural world. And you have some observations about the temperature, and then you want to predict a probability on raining. So you get all of these inputs, and then these inputs turn into some special features, and then you have an output. Okay, it's probably going to rain provided X, Y, Z. There's also some domains where you would have, you're trying to maybe, in this case, classify, you want to classify these data points in a high dimensional space. Let's say in this case it's 2D, but you can imagine it's in a high dimensional space. On the anything but the last column is what I was referring to as traditional machine learning. So these methods perform well in a lot of cases, but they usually hit a wall in terms of accuracy and ability. So if you can see here, this problem has blue points or red points, and you're trying to classify, all right, how do you divide the space into what should be belonging to the red points and what should belong to the blue points? And, you know, if you apply, let's say, nearest neighbor, you can see it's kind of it's sort of accurate, but it's not a smooth kind of what the human would expect. Okay, if it's a point here, then it should definitely be in this class. You could try maybe decision trees. You see the boundary is not maybe a natural kind of curve, which maybe that's what the actual distribution of this domain is. Whereas when you see on the right here, these are the neural nets. They are able to adapt into different kind of space dividing strategy. So they're quite versatile. And the inspirations for these neural networks. So these come from our understanding as humans. We try to find what is the sort of smartest thing or the best CPU that we know of, and we get inspirations from that from natural brains from animals and so on. So nature has this uh, fairly advanced system or CPU that is able to learn and actually act on the natural world. So the kind of the simplest unit is a neuron, and what you have is a cell that is connected to other cells and other things, and there's chemistry inside, and so you have inputs. This is just a conceptual, very simplistic way of looking at it. You have inputs, and you have some kind of small processing going on, and then you have outputs, and then the outputs get picked up by another neuron, and so on. The summation of all of this would result in a understanding or an action. So let's say I saw something, the photons drop on my eyes, the eyes send the signals to the brain, has a picture or a model of the real world, and then parts of my brain maybe will do the recognition and say, okay, and then a lot of cells would add up together, and then they will say, yeah, what I'm seeing right now is the computer screen. So this is a computer screen. Then it will maybe move it onto a control unit or part of the brain that would say, okay, there's a screen here, I'm going to look at it. I move my muscles to look at it. So that's a rough approximation of what we would understand about this complex system, the brains in general. So what people are trying to do is this super simplistic way of capturing this system, a neuron. So you have input signals, and you have these weights. So these are just numbers. All of these are numbers, but they're ordered, or the operations that are applied in a certain way. And what you do is you sum up all of these input signals, and maybe you subtract or add a bias, and then you take it into this. I'll talk about this later, the activation function. But basically, you have inputs, you have some processing going on, a function happening on these inputs, and then you have your output. So once you combine all of these, this is what you get as a neural network. It's a network of neurons. And the deep neural networks are sort of deep or many layers of hidden layers that are connected together. So you have layers of nonlinear processing units, these neurons, for feature extraction and transformation. So let's look at this. This is very conceptual. It's not real. You have an input, a dog. So you take the pixels, and then maybe the first layer would find bright, dark pixels, and then it would connect to the next layer, which is tuned to find the edges in the image. Later, layers would combine these edges and see, all right, there's a shape here that looks like maybe the dog ears, and then maybe this sort of high level identification of features in the image. Let's say, all right, I've seen an eye that looks like so, a nose that looks like that, four legs. Then the probability that this is a dog is high, and that's what my output would be. So this is a very rough description of it, and I have these basic demos that we'll look over. Can you guys see the browser screen? Okay, all right. So this is a very nice demo. It's from TensorFlow. It's called a Playground, a neural network playground. And it shows some of the data sets that I was showing before. So let's start with something simple. And here you can kind of turn on and turn off some of the features, add neurons, subtract hidden layers, and so on. So if I run it, it will start to learn the distribution or the space here and learn a function of how to divide points when it sees them. So you'll notice this is not a very good performant network. So maybe I'll give it more clues, more hints. You know, it's kind of getting better. Here we go. It was able to capture this complex this distribution. If I add something more complex and let it learn, now it's doing its learning. So this is the structure. These are the weights, and the kind of the combination is a neuron, and these are the outputs or the features going through the hidden layers, and that's the output. As we can see, this is not good. So for this problem, maybe I need to, increase the processing power of this model, increase the number of parameters. You can see slightly better. I'll add some noise. I'll add maybe a hidden layer. Run it through.
Dr. Ibrahim,
Yes.
at a conceptual level, how do you tell that the results is good or bad?
I will talk about this later, but in here in the playground, you could see this kind of graph, and it's showing you a loss. It's called loss here. And if it goes down while it's training, and then you see, all right, if this point is right where it should be, because you have, this is a supervised learning problem. I didn't mention that, but you have, points, blue points should be in the blue space, and orange points need to be in the, and you can compute a loss or an error on that, and then try to minimize this error. I think I just give it one more last try because I got it to train really well. I tried it last time. I think maybe it will do better now. But you guys can play around with it and see. Yeah, at one point I got it to exactly do this kind of loop distribution. If you give it something easy, it will immediately kind of solve it. And because this is a model that's more complex, then it has the capacity to capture the distribution better. All right. Another kind of visualization tool is this.
Dr. Ibrahim,
Yes,
can you copy the two links and paste them into the chat box so that I can share
absolutely,
it with everybody?
absolutely. Do you want it now, or maybe it's a distracting? Maybe.
Yes, it's up. Yeah, we can do it at the end.
Once we start the exercise, please guys remind me, and then I will.
Okay.
I will. Okay. Because in the exercise, I will leave it open for people to actually try it out themselves, because you could try everything in online on the browser. This is one thing. This is similar to the dog example here. So we have a picture of a coffee mug, and these are the layers that got learned. So this is a network that's already learned, and it now is showing you the processing that's going on. Let me click on. So let's take this. You can actually see, this sort of an intensity map, and it's, capturing maybe edges or other features. Here, maybe it's capturing redness of the image. And then it goes on and on and on. And then what you see here is, the espresso, the probability of what I'm seeing here as an espresso is high. If I try it for a bus, you can kind of just very roughly see that, this is kind of focusing on the yellow parts, and then maybe, the combination of yellow and lines and, tires or whatnot, and then it gives you school bus as the best label for this image.
Does the intensity of an image an intermediate? Can you go back to the previous example, please?
All right.
Sorry about that.
No problem. Okay, so let's say the school bus. Yeah.
Yeah. So the intensity or in the change of color in the image does it tell anything about the learning that is happening inside the neural network?
Yeah. So colors in general are almost immediately they turn into these sort of list of features. It's no longer just a concept of red. And the deeper you go in the network, it's more about a complicated description of a yellow bus with a green background and maybe some tires, and so it's really a set of features. So these are feature maps, right? And for a human, sometimes you look at something and then you really don't understand what this is. But for the network as a whole, when you combine all of these, when you subtract and add all of these features together, that will give you a description, give the network a description of at the end deciding, okay, this is a school bus. So for you, this is what they call, what maybe you've heard about, it's like this black box. So for a human, I don't really understand what's going on here. Maybe I can theorize about, right, this branch is looking at yellow things. And if I give you another yellow thing, maybe you can see it, right? This is an orange. And then here it's like, the neurons are firing up saying, oh, this is a red object, or a bright red object. So it gives out that signal. And then later on, it gets picked up until you get this orange description. If I do a blue car here, it's a different kind of response. So it's not as simple as this is one way to visualize. There's better ways to visualize what the network is learning and what layers are contributing to which part of the final answer. But you can kind of see it here. The bright yellow object here, bright yellow object. See here, it's also bright yellow object. So it's not about RGB. It's now some kind of maybe a bright yellow thing. Is that clear? Does that answer the question? All right. So what we looked at before, it's kind of a little bit a peek inside. You have images. In this case, this is just a digit 7 represented as 28 by 28 pixels, and it's just an intensity value. So 1, if it's super white or black, it's 0, or the other way around. It doesn't matter. And this is one of the layers that we talked about that maybe are focusing on the color or the edge or intensity. And what you do is you have these weights or parameters that describe a function that's applied on this image, and then that's the output. So these are 5 by 5, let's say, feature maps. Sorry, these are the weights. On the right here, we see the feature maps after you apply these weights on them. So that's a list of 7, but you have some kind of filters that are applied to the 7, and then you get these kind of representations. So the 7 is not just a single picture now, it's 5 by 5 pictures that have some kind of small clues about, all right, there's going to be a vertical line here or horizontal line here. And then you keep doing that. And then you can see they get smaller and smaller and smaller for this convolutional neural network. And you have this 36 channels of 7 by 7 pixels that are describing this. And this description is rich enough that you can keep on, building the network, and then you can have a classifier for these digits. So if I give an 8, I will get a different kind of set of features at this point in time that will ultimately increase the probability of this becoming an 8. And in the case of the convolution neural networks, what happens is you take pixels and their neighbors, and then you apply these filters, and for each filter you get an output. So for example, this 2, and the filter is -1 for the pixel on top, and -1 on this pixel, and +1 on this pixel. And then you do this computation, and then this is the output. This is the sum of it, is this output. So there's an animation here that shows this is, for example, an intermediate or the first input image, and this is the next layer on. That's what the image looks like, or at least one of the images looks like. So here we see the filter is these numbers at the corner. So that's a filter, and then you compute a convolution here, and you get this smaller image. And the reason you want it to be like this is you could in theory have it compute something that stays the same size, but what researchers have found out that you could do much more things much more efficiently if you decrease the number of parameters. Otherwise, you can actually not even start to compute once these layers are in the million parameters that you need to keep track of and you need to solve for. So
Dr.
eventually, yes,
I hope that you're not going to hate me tonight because I might going to interrupt you several times. Can you
no, it's
explain
fine.
for
So
us
it's all about
the
learning.
concept of thank you the concept of convolution because the
Yeah,
student they don't know it.
yeah, okay. I will not go deep into it, but this is how I understand it. All right. So a convolution is a function of a function, sort of a function on a function. But in this domain of deep learning, what you do is you can just think of it as a function that's defined by these weights parameters. So um, let's say that this function and this parameters are all 1, 1, 1, 1. This means that this convolution convolving this picture, if they're all 1, 1, 1, then it will take this 7 and then it will add you know whatever it's 9 times the value every time at each pixel, assuming we keep the dimension of this. So it's a function that is defined by these weights. So what we know as a function, for example, x squared is x times x. In this case, this convolution is a function where it takes this pixel element and then it applies a weights, filter weights, where it adds them up and gives you the summation here.
Okay.
It's not it's not a very intuitive, maybe the way I describe it is not very intuitive, but I think you could think of it as it's a function on this pixel, on this pixel grid. So you apply a function. Okay, what you could do, you could multiply by 2, just multiply by 2. Then all of these values become higher by 2, by a factor of 2. But what you could do is you could do, you know, what I said is you look around of the pixels and then you apply the operation shown in this filter, and then you sum the values and then you go to, and that's your output. So in this case, you see this dark blue um, sort of sliding window. It takes the pixel and the neighborhood, and then it applies this 0, 1, 2, 2, 2, 0, 0, 1, 2. The multiplying the value by this weight, and then each one of these you have 9 values, and then you sum them up, and then you put the answer here. So it's a function on this grid, but the function is defined by these parameters.
And the green square on the right, it's a set of features or?
No, in this case, it's the exact output for this filter. So if I see here, I have 1, 2, 3 filters. I should get 1, 2, 3. There's a missing here, but 3 greens. So an output for each filter, right?
Okay.
In this case, this is some intermediate, so that's why they're 3. This is confusing. But in any case, you can imagine that don't look at these two. Just this is your input, and then you have 3 filters. So 3 things you're going to apply to this picture, and then you have 3 outputs. Uh, 3 outputs. So this is one filter. The filter is this blue, dark blue area, and this is the output, and this is the input. The blue one is the input, and the green one is the output. And I will show another figure that maybe also I'll also point out what's happening here. What are the outputs for that? All right. So how do we learn? What's the basics of learning with this neural network architecture? What you do is you repeatedly feed training data into a learning algorithm. In this case, it's going to be usually just an optimizer. I'll parameter it. And you modify the bottom parameters, the weights that we saw before, in order to optimize or minimize, for example, minimize the loss function. So you have a input X and you have also an input Y. So this is the answer. So let's assume this is the question and Y is the answer. So I give you the question and the answer, and I give you also a way to validate an answer, an output of this function. So I give it a question, and these are the set of parameters, the weights that we saw. And then I have some loss function that says how far away are you from the reality, which is Y, the real answer, Y. Once I have that, then the optimizer's job is to modify the weights or the parameters of this, the kind of this, the structure of this network, such that when you run it again, the same example, you're going to get a less worse or better estimate output. So in time, what you have here, this is a kind of a common figure or something to always look at for, which is you have a loss. When it starts, it's totally random weights. The network knows nothing about it. It's never seen any examples of an answer question that you give it. And iteration in time, the optimizer will keep tweaking these dials, tweaking these parameters in order to ensure the loss keeps dropping down. And then, if you reach a super low point, then you can say, all right, this is my good enough or stopping criteria. And now I have a model that's learned. So I can take this model, and maybe the question and the answer is there a face in this picture? And the answer is yes for some sample I. Then if I give it another face, I will get a answer that's with some accuracy. So maybe 90% of the time, if you give me some specific test set, I will give you a good answer, which is there is a face. Now, if you remember what I talked about, this imperative functions, it's really, really hard for a human to come up with an algorithm that describes there's a picture. If I see a picture, there's a face here. So that's the nice thing about this end-to-end learning is I just give it what I do give it is the question and the answer and the way to find how far away are you from the answer. And then I just run a standard optimizer and get the output. So here's another view of this. Don't bother with the axis here. So let's imagine that this is a space, this kind of notion of space, فضاء الfunction or model. So this is a space of my function. So this is a function. Let's say this with the same example, the function of finding out there's a face or not. All right. Red means bad, means it's worse performance, and blue means it's really good face detector or face identifier. And what happens in the learning process is this conceptual moving in the space of possible parameters. So you can imagine if you have only 2 parameters or 3 parameters, let's say, only 2 parameters in this case, and your optimizer can jump around the space, like just assign random values for these parameters. And it will reach a point. So if it jumps, let's say over here, to assign the weights as weight 1 as 5 and weight 2 as 6, it goes here. It's a bad place. the optimizer will look at the neighborhood and perform this gradient descent. So visualized here where you look around each step you are and try to go in the direction that minimizes the loss. So you keep doing that, and that's the solving and the learning for this this optimization problem, where you reach a low point. Now, this figure is also showing us that this space has multiple points where the answer or the model is good. And sometimes you start training and you end up in this kind of local minima or area where you think you have the best answer in terms of when you muck up or change the parameters, this is the best spot. But in reality, you could be missing the super or ultimate or global solution, the best solution here. And this happens a lot. And for this simplistic case, this happens. And if you have millions, literally millions of these parameters, then you are possibly never going to get to this global, ultimate solution. So there's things to consider here about, okay, how do I try to increase my chances of learning better and finding a better minima than this one. This is where the optimizer kind of optimization and optimizer research is looking at. And all of what I've described, I think this YouTube channel, 3 Blue, 1 Brown, it's a mathematical teacher, and he has this series, just 3 videos about neural networks. So, but what is a neural network? And it does explain all of what I talked about very beautifully, and it does also explain convolution neural networks, and convolution is even maybe better than I have it. So I highly recommend this series from 3 Blue, 1 Brown from YouTube. Other sources of learning are online courses, and this is I actually took this Udacity course. That's kind of my intro to the field of deep learning. I've taken a couple of machine learning classes, but they were all talking about the classical machine learning methods, and they only mentioned neural networks. It was not something that was practical or useful. So later on, people are picking up on this deep learning, and then you could take courses, Udacity, Coursera. It has projects. It actually gives you a certificate, or sort of they call it a nano degree. They have a lot of staff helping you learn. You can ask them questions. And there's also a series that's very practical, very hands-on from the Fast AI people. And the first course or the first lecture, they tell you how to create a classifier, a model that looks at a picture and tells if it has dogs or cats.
Just for
Right
fun,
from the start.
why is it advertising itself as making neural nets uncool again? Does this have to do with the uncool history for neural nets?
I don't remember if he talked about this one, but I think he's trying to say that it's boring. It's very simple. So it's like, oh, it's so
Okay.
simple. It doesn't need a kind of sophisticated special person to know how it works. So it's just
Okay.
like, oh yeah, it's like a k-means algorithm or something. It's very simple. I think that's the attitude that they had in the course. So yeah, I actually went through the Udacity course and the Fast AI course. There's also, for people who are still using textbooks, there's a bunch of them. Unfortunately, with this textbooks is they, and in this fast-moving field, almost all of them would have some kind of old knowledge or something that's completely not used anymore. But some of them that talk about tools are kind of useful. For example, there's these 2 series that are online, they're free. And they have a really nice way of describing, even the concepts of the deep learning and the functions that you apply. So I recommend this Neural Networks and Deep Learning by Michael Nielsen. Other online sources, and these are sources that I use daily, almost daily. our archive.org. This is a place where people put sort of scientific papers, or they should be, or they started out as kind of reports or repository of research and reports. But now there, it quickly became into this. If you have something fresh still going on, a paper, and you want to put your own work out there just to kind of be first or advertise it, then you put it on archive and then people tweet it out. And it's just a totally different way of how things used to be, where you have to wait for a conference, you submit it, you get scrutiny over it, and then you get published. Now it's all, post on archive, link on Twitter, discussion on Twitter, or discussion on Reddit. I actually visit this Reddit machine learning, and there's always something fresh or new, and it's also nice that it covers multiple things, not just for me computer vision. It also describes things like speech synthesis or um, other topics. You can also find a lot of tutorials and examples of people actually implementing things on GitHub. So you could say GitHub, deep learning model about identifying or translating Arabic to English or something. You could find something there with and with that is also this Medium articles. Probably anyone who've searched on any topic of deep learning would end up in some Medium article about deep learning. There's some kind of nice visualization uh, online resources. This Distill has very beautiful representations and visualizations of neural networks. This also has some kind of interesting new research ideas. And also following some of the kind of industry or lead scientists in machine learning. So Kaprathi, Yann LeCun, Hard Maru, and this last person, the name is Roadrunner, but he's very, very quick. He's probably the quickest person to identify a new research and immediately post maybe pictures, tables, or code. And I also recommend, if you follow them, if you right now go to this Twitter, you'll see very interesting research. I'll show some of it in the talk. So we looked at resources. Now we'll move on to architecture. So neural networks. So you have this neuron, this convolutional layer. How do you come up with a neural network? How do you create a new network? So a little bit of history. What happened in 2012? You have this AlexNet that was a neural network method that was able to beat all of this classical ways of doing machine learning, of clustering, whatnot, in the challenge of identifying objects. So there is a challenge of 1,000 classes. So, different kind of dogs, a human, a backpack, food, a banana, apple. It is 1,000 classes, and then you give it to the model, and then the model has to accurately find, okay, this is a car, this is a boat. And AlexNet was able to beat by a large factor what was the state of the art, what was the best performing models at the time. And this is due to multiple things, but there's also one factor about the compute power. So in around 2012, NVIDIA and all of these GPU big corporations, they were producing, very high capacity compute chipsets, and it turns out that these GPUs, the graphics processing unit, are very well suited for the way you can do this optimization, this learning for the networks. And so we can see, very quickly, people were trying to find efficient. So this is a number of operations, gigaops, and high accuracy. So in this figure, but this is probably an older figure, the best performing model is this Inception V4. And these are older ones. They had a lot of parameters, but that doesn't mean they were good. So there are other things in consideration that made, these networks much better with the almost same number of parameters. This BGG is also very old. had lots of parameters, but not the best performance. So how do people come up with these networks? There's this sort of people building up on past research. So they find, okay, AlexNet had this tweak that I could do to it, and then I can find this, BN AlexNet in the training, or adding a patch norm layer. Then people will say, hey, how about if I, change the connection? So if you look at this picture, this is just a conceptual neural network. It's probably very old and nobody's using these kind of architectures, but you can see, all right, if I connect it this way, if I connected if I add a part of the network that, maybe upscales the image or increase the number of layers at some point, and then go back to decreasing the number of layers, and so on. And then you experiment with these, and then you have maybe a set of tests, and then you run them, and then you get a better result. This is a very simplistic way of how would you go about and pick the right architecture. The sort of the cool thing going on now, if the future is actually letting a computer design its own architecture for learning. So if you are Google and you have a lot of processing power, you actually do either randomly or with some set of rules, and you say, okay, I'll try this unit of processing, and I'll connect it with this unit, and then I'll compute, the performance of this network. Then I'll drop this, and then maybe I'll add this and add these two units together. And this is what Google's auto ML, auto machine learning, is all about. And this is sort of this is the latest direction of finding out architectures. But a lot of work are based on successful architectures, and then people try to add some modifications on them. For convolutional neural networks, this is most of the examples we saw before. They're used for image processing and video processing. Things to kind of keep in your head about this field is ImageNet, which is the data set that AlexNet we're using. It's a large set of 1 million natural images divided into 1,000 categories. So it's a image is a question, and the answer is there's something in that image, or the biggest thing in that image. And there's a million images, and so you can see this is a big data. With big data, that was the promise. With big data, I can surpass human ability. There's other categories of data sets. This Pascal is about object bounding boxes. There's places too, which looks at indoor scenes, and maybe this is a living room, bedroom. This is useful maybe for robots. And a kind of winning architecture is this encoder decoder, where you take the image and then you can see this kind of slab or 3D layer that has a thickness. This is just a conceptual representation of what's happening. So you take an image, then you multiply with the filters, like I said, and then you get these feature maps. Each one of these is a feature map. So, and the red one is just a polling operation. I'm not going to go into the details for that, but it's an operation. But if you look at the white ones, these are feature maps. So this dog image at this point in time is fully described by, let's say, 14 by 14 by, maybe 100 layers. So it's a tensor. So it's a matrix that is not just two-dimensional. It has a third dimension, and it's just numbers. It's just numbers. But these are what's special about these numbers is they come out at this point, and maybe you have a rest of the function learned that when it sees this representation, this encoding of this image, this kind of rich encoding, then these numbers are not random or meaningless now. No, they mean something, because once I plug them into the decoder, it's going to translate, in this case, maybe find the dog in the image, this purple segmentation. And this is actually the exercise we're going to work on.
So these numbers are the weights associated with the nodes?
No, and at this point, these are the outputs. So the intermediate outputs in the network. So there's weights. The weights are not shown here, But this is the kind of the output after applying the weights on.
So the output of one stage that is fed to the next stage.
Exactly, yes.
Okay.
Other architectures that are interesting and important, but maybe in a different field, are recurrent neural networks. So what you do is you have, let's say, this is kind of box, so it kind of abstracts. There's a complicated structure inside of it, and in this case, this is a spell autocorrect, or finding out the next letter. So you start with GR, and then it will maybe give you a recommendation about EAT. Great. And the way they do it is they have to feed a series of inputs, but also look at intermediate outputs from the previous input. And this is for recurrent neural networks. So there's sort of the same network gets fed from a previous state. So it's multiple state, and then you try to learn a network that no matter what letter you give it, maybe it will look back 3 letters behind and then kind of give you the 4th or 5th recommendation for the letter. There's also another interesting architecture that's kind of maybe mystical for some people, is this generative adversarial networks. And this is an interesting architecture because what happens in this architecture is you have 2 networks, this blue and red, and what you do is you kind of pit them against each other. They have to sort of adversarially try to optimize and perform a different goal. So what are these? We have a generator network and a discriminator network. The generator network takes literally random noise. So just every time it takes random noise, and it feeds into this convolutional neural network, and then it outputs a figure. Of course, the first time it doesn't output an 8, it outputs some rubbish, random things. The discriminator takes real images, in this case 1 maybe, or 4 or 8, it doesn't matter. It takes things from the real distribution, the real set of images. And then what it does is just a simple thing where it takes the image and then, feature map and convolutions, and then it just tells you that this image that I saw, a single image, is real or it's fake. So you have these 2 networks, one trying to trick the other, and the other is trying to learn the reality of, okay, what is a real and what is fake. And what happens is this generator becomes so much better at generating fakes that it will actually generate something that's confusing to the discriminator. So it will say this is real, although it comes from fake. And at that point, you're kind of reached a point where you have something that once you feed it noise, it actually generates something that looks like the reality or things that you've seen before. And these at the bottom, each one of these pictures are completely fake. So how do I generate this? I take literally random noise, just set of random numbers. In this case, it's 512 actually for this exact method. 512 random numbers. I feed it into this generator. It applies a function, like we said. This is the network. You can think of it as just a function, this super complicated function. And then you get a human-looking face, which is quite remarkable, very realistic. Maybe it has some problems and mistakes, but overall, very convincing. So GANs are very interesting architecture. Yes.
So these pictures are not of real people. They are generated by this network.
Yes, exactly.
Oh, very
They
impressive.
look, they look very real. And this is not the highest quality. There's actually a step further that's higher, even more interesting. So this paper is called Progressive Growing of GAN, and then later on they called it Style GAN. This is the new name for it. Is actually very interesting, and there's now maybe hundreds of papers just from this work. They try to do things like take your image and then put it in this network and then modify it. I'm sure a lot of you have seen Face App. this app that maybe makes you old or adds a smile or uh, adds hair, changes your gender, and this is using this technology, GANs. Other architectures, I won't go into them in details because in graphics we don't have much success at this point with our reinforcement learning, but it's very important in the area of robotics and games. Having a computer that know how to play a game. And playing a game is very useful to study because you can apply a real world scenario as a game. So let's say you want a model to learn how to sell and buy stocks. So you can make it like a game, and then the network will try to win by making more money. In this case, for reinforcement learning, what you need are a couple of components. Most importantly would be an environment. So you need to have, in the case of a game, it's just the screen of the game. It has different things or conceptual things inside of the environment. But it could be very detailed, like if you imagine games like Grand Theft Auto or Uncharted, they look very realistic, and the animation is realistic, the scenery realistic. So you can have an environment like that, and then have an agent run around and perform something. Maybe like just walk or pick up things, drop things. And what you do is you give it a reward. So this is kind of like teaching a kid how to learn a skill. And then you give it a reward, or you give it a kind of a negative kind of reward in terms of, oh no, you did something wrong. So you imagine you're a robot, you're walking around in the environment, and then you fall off, and then you get a bad signal of falling off. Or if you walk for a long distance, you get a high reward. And then what you do is you update a policy. So, if I see the situation, if I see an environment, there's a road, a straight road, maybe I should walk on it, and that will give me a better reward. And that's the type of policy, that's the type of actions that you want to learn from this network. So in games, it's usually, okay, I see the screen, maybe multiple frames or single frame, and then I move the controller left, right, and try to score more. So this is for reinforcement learning. In terms of frameworks or the tools for learning, or teaching networks, building networks, there's a different set of frameworks. They come about because of this kind of large institutions, either academic or companies like Google, Facebook, where they have their engineers and they're trying to say, all right, let's make something that works best for us, or they experiment with different ideas. So this is why we have multiple things. Maybe MATLAB, they have their own, Microsoft their own. TensorFlow is Google sponsored. Keras is by one of the engineers at Google. It's just kind of simpler TensorFlow. And PyTorch is from Facebook. So this slide is kind of old, but things changed quickly. And what happened is that everybody's sort of converging into a state where you have multiple ways of designing networks. This kind of a dynamic graph or fixed graph, computational graph. But in general, what people seem to be, for beginners or even advanced researchers, for flexibility, PyTorch seem to be winning a lot of hearts. And a lot of people are gravitating toward PyTorch. TensorFlow had to give up on the idea of, or not give up, but kind of adapt to allow for how PyTorch is, how the framework works to attract people. So I think PyTorch is a good, right now at this stage, is a very good framework. Might be the one you use in your project. And the other one that's also easy and also performant is Keras, which is, again, it's just based on TensorFlow, but it's a nice way of building TensorFlow models. And this is the one we're going to use in the demo today. Things that are good to know about is there's actually an initiative between AWS, they have their own framework, and Facebook, PyTorch, Microsoft, CTNK, and a whole bunch of others where they want to allow conversion. So once you build a network, in theory, ONNX format allows you to translate from one model to the other. However, in practice, it's usually there's always a kind of a edge case that doesn't allow you to go forward. A big consideration, aside from network, the frameworks, is the resources. So compute resources. These networks require on the order of millions and maybe billions of parameters, just the parameters. And for each parameter, you're doing, the operational learning maybe a million times over. So you need something that is powerful in terms of compute capacity, and you need a lot of it to do this computation to learn faster. Otherwise, on a single machine, you might need months to develop and learn your teach your model. So there is this very important aspect of it is this cost of deep learning, what it actually costs in terms of dollars. And some solutions you could look into are renting cloud time. Unfortunately, it's still very prohibitive and expensive for a an undergrad or a master's student. And ideally, if you're in a situation in a university or a research lab that has a lot of compute, then you can be very effective. So there's kind of a divide of who can do deep learning and who can't, which is unfortunate. And there's also some phenomena now where Google and Microsoft would have these kind of crazy $1 million training sessions. So it's just $1 million for maybe a month or something of these machines running. That's the equivalent to get a model. So to put that in perspective, let's say we'll take one of these, $1 an hour. If I want to train this model, it will take 8 machines, so $8 per hour times 24 times 7 just to get to this quality. And that's the cost of me training this model. I don't know who's quick with math. How much was that? Maybe someone can provide an answer. But this is just an example for that. Here you can see 80. Yes.
One around $1,300, I think.
Yeah.
So yeah.
Yeah. But this is if you know what you want, like the answer of how to train this model. Imagine we talked to the people who invented this model, and they have hundreds of what I said, so $100,000 worth of compute every day. Of course, they don't pay that because what they do is, the equation changes if you buy the hardware and keep it, then you can utilize it more as opposed to renting it. And that group was actually NVIDIA, so they get much cheaper hardware. It's kind of unfair that if you're a company that builds the GPUs, then you will always have hardware available for cheaper than other people.
There is this comment on from the chat. It says Google Colab provide good set of GPUs. What's your opinion about Colab, Google Colab?
This is the perfect time for because on the left this is the logo. This is Google Colab. So the solution for kind of practicing and learning is what you could do is you either pay for a cheaper service. So there's this Paperspace that gives you cheaper hardware, relatively cheaper hardware. Of course, the best thing would be to actually own the hardware and just try a lot of experiments. Or in our case, if you have a machine learning, a whole department working on that, KAUST spends around millions of dollars each year upgrading their cluster of processing cluster. So the whole department shares this sort of supercomputer, GPU supercomputer. But for you could, as a single individual, you could, or trying and experimenting, you could either buy a month worth of credit on Paperspace, or you could try Google Colab, which is totally free. The only catch with Colab is you only have single GPU. So some of these models do in fact need multiple GPUs, or otherwise you have to teach it for a long time. So let's say something takes a month to train on 8 GPUs, it will take you 8 months to train on your own. So that's a big difference. Single GPU, the GPUs are usually old, so new models would need more memory, GPU memory. So maybe you cannot run the model because it's just you don't have the memory for that. It's free, but it's limited in terms of capacity, power, GPU power, memory, and also you have a time limit. So the practice here is that you save checkpoints or kind of intermediate states of the learning process, and then the machine will actually turn itself off because they're giving you for free. It's sort of unused hardware, and then they give it for free to. It's kind of a community service or service to the community. So it's very unlikely that you can invent or write a paper in Colab. It's usually I've never seen an instance of that. The opposite is more true in terms of if you are a deep learning researcher and you have a lot of hardware, you have some kind of advantage over others because you can try multiple things. Like I said, there's a almost infinite ways to combine things. And if you have the hardware, you can keep exploring and trying different things. But today we're going to play around with actually Colab, and I will show you a full example that runs in 20 minutes. Some of you have seen this before, but maybe for YouTube audience, I will talk about one of my favorite sites. And this will give you some kind of view of what are the machine learning tasks that are people looking into. So this website called Papers with Code, and this is the homepage of it. And what it shows you here is at the homepage is these, or sorry, not the homepage, but the state-of-the-art page. It shows you different categorization of problems, general problems in computer science or something that humans want to solve for. So, it could be anything like, here, music generation. It could be audio classification, audio generation. It could be playing games, real-time strategy games. And for us, or for me, the most relevant is this computer vision tasks. And you can see there's about 801 subclass of this problem. So if you had things that deal with 3D or geometry, things that are about segmenting scenes, labeling pixels to belong to something, things about generating, that's the face work that we've seen before. Yeah. And there's super resolution. There's just so many of them. There are video things like understanding the video, tracking objects in the video. And actually, the homepage of this site, Papers with Code, so it's highlights papers and the papers have code, is this kind of trending tab. And we can see here is 2012, 2020, 2020, 2020. These are recent papers that are very interesting, and people are showing interest by these stars on GitHub. That's how the site measures interest. You can see this super resolution paper. I will show a video of this human digitization. There's more work on generating high quality faces. This is the site I showed for visualization, and so on. Things for self-driving cars. So this is what the like I said, see, this is an older, like a year ago, and now it's already at 800 tasks, sub tasks of computer vision. And with this papers with code, you can also keep up to date on what is the state of the art. Sorry, I should mention that because they have leaderboard on the subproblem. So let's say image classification, and it's sorted by data sets. And this is the ImageNet 1 million image that we talked about. And you can see here the time, as the time goes by, the accuracy of the test is going higher and higher. So the best networks are usually modern ones, and they're on the top here. And incidentally, just because something I always try to advertise, the best network for image classification that can also be used for many tasks is it's called EfficientNet. And EfficientNet has 60 million, around 60 something, 66, yeah, let's say 66 million parameters. So 66 million numbers that's just in the network, and ways that they are connected to each other, ways that describe a complicated function to get an accuracy of 85% on the ImageNet tests. So that's the shape of the networks that we are dealing with.
Dr. Ibrahim, I wanted to ask you about the concept of parameters on a previous slide, but since it's mentioned again here,
yeah.
Can you give us like a definition of what exactly do you mean by a parameter?
Yeah, so a parameter, I'll say it briefly here, but we'll also see it in the demo. So parameter, and let's say if we keep this in our mind, so a parameter would be these weights, or let's see in this figure, these weights. So there's 6 million of these weights, right? Here, this exact filter has 9 parameters, right? So this is 9, they're contributing to the million, and then there's maybe hundreds of layers. And then each layer would have multiple filters. So 100 by 100 by 9. So maybe you can have a network with 9 million parameters. So, and these parameters are like here, they look nice and clean, like -1, -1. But in reality, when they learn, they turn into they're real numbers. So they could be -1.2355, some kind of real value. And it's unexpected. It's not very simple to explain what this set of weights is trying to contribute to the overall goal of learning. Like what really does this represent? In itself, these set of parameters are very hard to kind of pinpoint what they're doing, but the combination of it as a whole, when you look at the network as a whole and the performance, gives you this complex function that learns that maybe this number is a 7, classifies it as a 7.
Okay.
Okay. Another website I mentioned before is Dataset. A big part of I'm gonna leave this. A big part of learning is data, or a success for learning is to have the right data. So the right examples, the right questions and answers to give to the model to train. And there's this website called Visual Data that tries to list a lot of very variable sets of data that could be people, with marks on the faces. It could be, some kind of medical things, airports, um, things like maybe brands, or here we can see yoga poses. It could be things, more medical things. It could be data about like this COVID-19, maybe who got infected and where they were living, and what's their medical history. There's things like people marked with question and answers, or the ground truth of an answer of the question. So maybe this person is wearing, a red shirt or something like that. So yeah, there's a very big repository of all of the data. It's mostly linking to it. It's not saved in it. But people get creative and they can combine different things, like data from this problem, and then maybe I can do something about it and turn it into a data that's useful for another problem. There's an interesting paper, interesting data set, Arabic handwritten characters. So this could allow you to have a model that learns how to read Arabic words. Um, yeah. So that's for data sets. I wanted to highlight some kind of very recent papers. And on the left here, we see the latest version of the style GAN, the GAN that generates human faces. And in this instance, what it's doing is everything you see here is completely fake and generated from random noise, even the top ones. And what's trying to do here is to do this kind of combining different things. So it will combine here, this is a male, 40s maybe, this is a woman, this is a child, and this is a female smiling. And then on the left here, you give it a style. So this person maybe of Asian descent. Now everybody's is sort of looking at more Asian. Here is Caucasian, dark hair, and it's actually combining that. So this shows you sort of a traveling around the space of possible outputs by modifying the input. And some of these results are quite remarkable and something that was not ever achieved before this kind of deep learning research going on. Another thing, this is very recent, this image compression. So maybe some of you have studied this about compressing images and data. And if you compress an image, usually if you have a lossy compression, so you can kind of give away some of the accuracy. And maybe if you do save a JPEG, super lossy, you get this 70 kilobytes for this big image. However, if you use I think this is GAN based also. Yeah, it's generative image compression from Google. You can get even less size, but the image is so detailed, it has so much color, and it almost looks like black magic how it's happening. But in reality, what you do is maybe you save the image in some representation, and then you save, like we said here, in some random vector, but in this case, it's a specific vector that once you feed it in the network, it outputs, the outputs is not 66 kilobyte. This is just a representation. The output would be a high quality, big image. But it's kind of reproduces the textures and the details on the image. So you can imagine you could do 4K video with much less consuming of data. Here's another cool paper that's trying to do something that people would imagine is the next step in photography, doing this 3D time frozen shots, and you can even run the time and move the camera around. It's kind of cool, but this requires a very expensive hardware as of right now. But maybe in the future, your cell phone could produce an image like that. There's also on the right pictures about digitizing humans. You can see very accurate representation, a 3D representation of it. And this would be cool maybe in virtual reality scenarios where you can have yourself shown in the space of someone else on the other part of the world. There's useful things like image colorization. So, this is actually a cool project if someone is still on the fence on their project, is to take all of this historical Mecca, pictures and then try to colorize them. There's things like, this is an interesting work where they learn from a small example, a person and what, and the spoken words, spoken signal, and then they try to maybe read the lips and generate the audio, which is useful if you have a live video and it cuts out, like the audio signal is cut, then you can fill in by just looking at the lips, which is very interesting. Or you could read someone from far away. Maybe it's a system to assist people with the they have bad hearing, and then you have a camera or like something like Google Glass, and then it will try to capture just the lips, not just the audio, and try to amplify it with the lips and try to generate it, to generate back the words that has been spoken. This is kind of a shameless self-promotion about latest advances. These are 3 papers that I've worked on. The first one is depth estimation from a single image. So you have a single image and you want to generate a 3D scene. Let's show how it should look like in the real world. I'm proud of this work because at some point it used to be the state of the art. So in the entire world, it was performing very well. Now it's probably some other works have already passed it. We also worked on this high resolution texture synthesis. So we were building, a new Earth using these GANs. So synthesizing a very detailed Earth. And something of interest here is that we were the first to do gigapixel size images. It's very, very high resolution, maybe 30,000 pixels by 32,000 pixels. And this is kind of a sneak preview of something that I'm working on, this detexturing, I call it. And on the right, you can see what's happening here is you feed it a real image. This is a restaurant, maybe a coffee shop, and it has some texture and things and promotional things. And then the network actually produces this output, which is sort of erasing all the texture. In the next example here, you can see it's looking at windows and thinking it's a texture, so it's completely blocking out the windows. Here, the wood is the texture and pattern is also completely blocked out. This human becomes a kind of shaded representation. And why is that useful? Because this is kind of ties into the depth estimation problem. So if you have this representation of the same scene, then you have more data. So this is a way to generate more data to help with the learning. Okay, so that's an hour and a half. It's a little bit over time. So let's start with our practical portion of the talk. Before that, I will send the Zoom chat. That's what you wanted, Doctor? Okay. All right. I can also send the talk at the end. Chat. Okay, everyone should get it now.
I'm going also to post it into YouTube.
Okay. Yeah.
Okay, the slides. I think you will be able to share with us the slides.
Sure. Yeah.
Thank you.
All right. So what's our tutorial? What's our task here? It's going to be object recognition / segmentation. So this is an example of a real system or a real model that learned how to look, at the street and identify things. So here's, it can identify an umbrella, a person, a backpack, a bus, street. So why is that useful? It's kind of cool because it's informative. If you're a robot or something, then you can tell what's around you. Maybe it's a system to help people, with poor eyesight. They can listen to what's around them and see the world through this kind of a representation of words or sentences. Or it could be let's imagine this is a self-driving bicycle. So a bicycle that automatically drives itself, or a scooter that drives itself around. It really needs to know when you drive, needs to be aware of what's around you, what's the surroundings. So there's people here, maybe I need to slow down. There's a car coming, I need to see it and process that, how to act based on that. So object recognition has lots of applications. And for our case, this is kind of a sort of a simplistic way. If you look at these 2 pictures, let's assume this is a security camera of a public place, and you want to identify some kind of dangerous or suspicious things going on in this picture. For a human, if you just look at it, you still kind of have to look around left and right to identify it. If you train a model, on lots of these security cameras, the model will immediately spot something suspicious. Maybe this is a radioactive thing or some kind of a weapon or sharp object here. So this will be so the problem setup is that you have the real world and you have actors or things moving around, and you have dangerous items that you want to classify or identify or segment in the scene. The architecture we're going to use is, again, this kind of encoder-decoder. So it used to be called UNet, but the general term is encoder-decoder. And in this case, this is an example of it in a medical setup. So let's say you have some kind of interesting thing, a cancerous area or something, and you want to label it. So this is what you feed it. You feed it the question or the input and the answer or the output, the label. And you want the network giving hundreds of thousands or millions of examples to tune itself, change the parameters such that when it sees another new example, it will give you the right output. So this masking of some interesting points. I'll try to cover things like the data challenge, the model and the architecture, the optimizer we're going to use, and the objective or loss. And these are kind of some major pillars in every machine learning, deep learning model. So the code is here. I will also share it in the chat. And then we're going to use Colab to so if you open the link, you'll see this new GitHub view. And here you can see Colab demo. So I'll open it. And these are called Jupyter notebooks. They're kind of very nice way of showing. It's kind of like MATLAB. You have cells and then you run them, and you can kind of interactively start to code and play with things. And on the top here, you see a button that says Open in Colab. So this is a nice feature from Colab where you can write a notebook or a lab book, and then you can upload it to your GitHub repository. So one important thing I need to point out is to make sure to run the GPU runtime type. So runtime, change runtime type, and pick GPU if it's not selected. And press save. It might restart or do some stuff. And you can see the state of your machine here. So now I have the code, but it's not running, so I'll run it. So I'll say runtime, run all. And you can see this kind of animation going on. That means something is happening. It's queued and it's going to run. So all right, let's talk about this exercise. First thing is, in any problem, in any machine learning problem, is the data. That's the thing that will make or break you usually. So if do you have data or not? I tried to kind of make this more complicated than it needs to be, but I thought it was cool to be able to generate the data. So actually, this image is generated by computer in kind of script or program, and you can play around and change the type of emojis you use, the backgrounds and whatnot. This is not very important. This is not the important part of the code. So when you run it, it's going to take a couple of minutes, but this is just because it wants to install this library, and this library will help us draw the sample data, the data set. So I'm going to use something that's already computed and skip over
Dr.
all of this.
Ibrahim,
Yeah.
can we go over the program block by block, since already we have we can
Yeah. Yeah.
and then
but
if you explain for us the input to the block and the output of the block.
Yeah. But I'm gonna skip. I purposefully skip this block because it's doing it's just compiling and doing things. It's not. It has nothing to do with machine learning or training a model or something like. So we'll assume we have data, right? I'll go maybe over these scripts that generate the data, just because it's kind of a cool thing to try out. Generate your own synthetic data. So this is of course Python. It's a notebook, and you run Python code in it. At this point here, I'm just importing the OS library and then just a make directory command. So I'm making 3 directories. You can see your file structure here. Fortunately, so because if you don't touch the notebook, it disconnects. So all my files are gone for the past experiment. But you can see the data here. So once you create these directories, you're going to see emoji directory, PNG, and data. And what I do here is download SVG files. These are vector files from a repository. I already know and find which repository has all the emojis. So I pick an emoji, I download it, and then I convert it from this vector representation to a PNG. There's already a PNGs available of each emoji, but I did this because I want to play around with the size of the image. So this gives me more flexibility to do so. So what I did here is I specify locations. This is going to be the background. So camping emoji, beach, desert, park, and this is the emoji code. And then I specify actors, man walking, just people,
So
women,
you are
animals.
labeling the data here.
Here, I mean, it's just a kind of a human-friendly way of emoji because this emoji, I don't understand what this is the emoji code. That's the actual character for the emoji.
Yeah,
So
but you are
maybe you
not
can
going to
see it
use
here.
these labels at a later stage
Yeah,
in
no,
your solution.
no. It's all going to be pixels and just pixels. We're going to
Okay.
deal with pixels and images.
So it's
So
unsupervised learning or
no, it's going to be supervised because I will
supervised?
provide. I haven't talked about the 2 inputs and the outputs still. But in this case, so camping, this is the emoji. And what I do, you can see it's empty in the background. So I actually add a sky, just a gradient. This is all just graphics, simple stuff. It's not, has nothing to do with learning. And then I add people in the actors, and I also have a set of dangerous items. So in this case, this emoji is, that's, the bomb emoji. I have a knife and I have a gun, I think. So, okay, this is what's going to happen. Before, what we saw here are just, standard functions that do simple things like convert and download a file. So I download all emojis. And I give it a list of emojis. I download all the locations, all the actors, and all the dangerous items. I then create a PNG file. It's just an image from a vector representation to an image, and the images are transparent. So this, you can see here, there's a transparency, so I can replace the background. Or if I drop it here, it's not going to be a white box with a bomb in it. It's just going to be the pixels. And there is sort of unnecessarily fancy way of distributing the objects. Like if I go back to here, I'm trying to spread them out so I don't put things as much on top of each other just to fill out the space. So I'm doing this Poisson disk sampling. You give it a region and some kind of density factor, and in the end, it just gives you coordinates. So it gives you p's, where the p is just xy. So there's a function that distributes, and I pick this region. I drop any region on the top because I don't want something in the sky. And picks points in the image, and then these points are going to be used later on to splat or draw the different things in the scene. These are just standard things like, draw a vertical gradient. I call this function draw sky. This just takes, I have some colors that are pleasing for a sky. Just you can see the gradient at the back here. And then this is the function that will generate the data. So generate random location. By location, I also mean this entire thing. So something that has a background, the sky, and people, and possibly dangerous items. I try to do it a little bit efficiently. I cache all the backgrounds. So I just load all image open. I open all the emojis in the locations. And then, excuse me. I generate backgrounds. So I create a sky, and then I paste the background. In this case, it could be this camping background. And then I add actors. These are friendly things. You can consider them backgrounds. These are the people and the animals. And like I said, I sample the space. So I get XY coordinates for every actor. And I add a bunch of actors after loading them. And then I also add here's the kind of the target we were looking for, the dangerous items. So every time I open, first of all, I cache them and then I add them. So you can imagine here for each image and images, this image, or this images array has all the kind of background plus clean or safe objects. And then I go in and then I try to paste. I do some kind of logic to kind of just change the distribution or be a little bit selective about where to paste things. And this is just for kicks. I added this simulated CCTV footage kind of a thing. This is, it doesn't show here. It shows in the other. Hmm. Did I close that down? That's terrible. Oh, here it is. Okay. So it's, for example, this is like a night sky scene. There's people, and you can notice the scale is different here because I'm trying to make it run faster. And this is the CTV kind of useless thing, but it kind of looks like a CCTV. So you can think of it in real life. You will have a real background, you'll have real people, you'll have real dangerous things, and you have extra things in the scene. So how do you code a function that takes this image and outputs, there's a dangerous item here. That's our target goal, that I want to identify dangerous items.
So
So
that's the input image.
so this is the, let's call it the question, the X, right?
Mhm.
And the answer is this image. It's a mask that shows you, bright means, this is it. There's something here. And black means there's nothing interesting here.
Okay.
So the input to the network is these kind of question answer pair. And that's why it's supervised, because it knows the answer for the giving input. Okay. So the input to our method is going to be patches, or collections. Let's say, we can't put everything at the same time because there's a limit on GPU memory. So you do it in patches. So you take maybe, I think the patch size in the exercise here is 64 images. So 64 random images that look like this and like the other scene we saw. Yeah, no, this one is already done. So this is another scene. It has a dangerous item here. This gun, this gun emoji used to look more dangerous, but all the companies decided to make it a water gun
Mm.
to kind of minimize violence portrayal. And so I have, this is one, this is two, and there's like 64 of them at a time. At the top of the tutorial, I actually specify my data size. So I want 10 data sets. Each has 1,000 picture. I can put them all in one data set. I just did that because I want to download and then kind of upload much easier. But in the end, it's going to be like this. So data, it's in the HDF5 format, and basically it's just numbers. This the entire thing baked already. So you drew them, you draw the pictures. You can think of this as a video file or whatever, set of pictures. And each picture also has the answer to the question, which is identify the dangerous side. Okay, so here I'm generating random locations, you know, based on the 10. So 10 random locations, the images and the masks. And then I put them in a in the array, and like a named array, and then I save it in the file. The file, this is how I save the file. It's dataset, the number, and then the HDF file. This is the library that helps with the data sets I'm using here. You could use different things. You can actually use NumPy immediately. NumPy is very important to learn about. This is the kind of the math library for standard math library for Python. Helps you build, matrices. This is how you represent pixels and crop, delete, resize, all with NumPy and another image library. Okay, so up to this, is this clear, right? We have a data set, right? A bunch of files. These are just images and the masks. So the questions and the answers. Now what we're doing is, so we save them. Now this is where the deep learning and then the learning starts. All of that was just kind of preparing data. In other problems, you already have the data, you already have the masking. Sometimes you have just the data, the X, and you ask someone, literally ask people, to label every single frame or every single instance with the answer. So maybe they'll put a box or something around your, sorry, like someone will label this and then they will save that. Then you have a ground truth. You have a question answer pair. So I have the data. Now I start building my network and thinking about the optimizer and starting the training process. So there's this concept of hyperparameters. This kind of distinguishes them from the parameters of the network, the millions and millions of numbers that or weights that will get multiplied and generate feature maps, and then feature maps turn into more rich feature representation, and then end up with the output. We have this hyperparameters. This kind of describes the parameters on a sort of higher level parameters of the network. So what are some of the hyperparameters? Maybe it could be something relating to the resolution of the input images. So in this case, I'm putting 128 by 128. So all my images will get downsampled or upsampled to 128 by 128. Why 128 by 128? It's just a parameter, and the performance could reflect based on that. So maybe I need a bigger picture to have an accurate output, or I don't have enough time. Maybe I'm starting off, so I start with something small. General pixels are general images from the internet are maybe a megapixel, so 1,000 by 1,000. But if I run that immediately, I will end up wasting time learning this high resolution model before I can validate it. Does this actually learn or not? There's this business of epochs. Epochs just means going through the entire data set. So going through all of these images here, the 10,000 images. If it's 10, do we say 10 times 1,000, 10,000 images? That's the entire data set that we generated. So one epoch is 10,000 images that actually went through the network and facilitated some learning. So parameters were tweaked, modified, changed, and on the hope that the objective is met. I talked about this batch size business, which is also a parameter that's important. A large batch size maybe contributes better. Sometimes it's not the case. And why is this limited to 64? Maybe I can do it 128. That should, in theory, make a better model. But I could be limited by memory. So the GPU memory is generally very low than what you know about CPU memory, which is if you have 16 gigabyte or 32. For GPUs, they used to be even much smaller. The best card you can buy in the store in Saudi, just in the store, in a physical store, is around 11 gigabyte or around 12 gigabyte RTX. And this is already a bad card for training. It's a low performance for training. And these collapse models are around 11 gigabyte, I think, so it's around the same GPU memory, and I can only go to 64. I cannot go any higher. Otherwise, it will complain about running out of GPU memory. But you can see the dilemma here is that if I want to increase the patch size, but I can't because I don't have GPU. So what do? I have only two options, and both of them mean spending more money, either buying a new card or renting a server that can allow me to train on bigger patch size. The learning rate is relevant to the optimizer where we said, okay, when you are in a state, you look around your neighborhood and try to move in the direction that minimizes the objective function. So if you have a big learning rate, you want to kind of sort of skip ahead and very quickly reach the point of that. The danger in that is that if you have a big learning rate, you often kind of jump around places and rarely maybe end up in the right spot where you need to be. The parameters need to be updated in that direction. So if you have a small learning rate, you can you can slowly kind of move around the space of the very nearby space of parameters, and then that will take you, safely to a better spot. If you have a too small learning rate, that's a problem because you might end up, staying in that same space of parameter and never exploring it beyond. So this is a very important parameter. It's the learning rate. How big of a jump do you move forward at each
Is it a
step?
parameter of the optimization algorithm or the learning
Yes.
algorithm?
It's what's the difference here? Is the optimization algorithm helps with the learning, right? So it's it's a parameter for the learning process, and
Uh,
you put it in the optimizer, or you assign it for the optimizer. So the optimizer needs to know um, how far it goes in each step in the direction of the gradient.
One of the questions related to that slide is about the derivative. So in such a setup, does the derivative play any role here?
Yes, yes, you're trying to find. So this is a function, right? And if you want to find the minimum of it, to say high is bad, low is good, then from just a natural function that has a parabola or something like that. I can draw a parabola up here, right? So in 2D, you have a function here, and that's your system. You can imagine the system here, and you want to be in this spot, which is the minimum. So how you do that, you're here, then you can compute the derivative here in the function, and then it will tell you how to go uh, to the lower state or
So from the
the
name,
minimum of this function.
yeah. So from the name, the gradient is embedded inside the algorithm.
So the gradient is the gradient of this function, but this function is not a simple gradient to compute. I mean, it ends up being a kind of simple numerical way of computing it, but in the sense of Math 101, or it's not it's because it's a 6 million or whatever, 10 million, 60 million parameter function. So computing a grading for that is not straightforward, right? Um,
Okay.
but what you're doing is, in a sense, trying to find a gradient to that whole function, the whole system. It happens with I'm not talking about back propagation and all this. For that, you can really get a much clearer picture with the resource I posted. These 3 blue, 1 brown. They actually talks about gradient descent and the learning process and back propagation, the algorithm used in most of these systems. So a high learning rate can usually lead to bad learning, and then a very small one can lead to kind of stagnation and stopping around the space and not learning much better. Learning rate is actually, there's maybe another hyperparameter, which is the schedule of the learning rate. So actually the best methods in most classes are some things that you start off with a high learning rate, then you quickly jump around, and then you in time or in epoch in each step, maybe you drop the learning rate and get to the, and like here you see the learning rate being fixed. Like just imagine it's one step with the same magnitude. But in practice, it's better to do, buck buck, to kind of two jumps, tick tick jumps, and then have smaller jumps, and then getting closer and closer to minimum, local minimum. Um, Another thing. Mm-hmm.
To, I have if you allow me, how do you know when you set the learning rate that it was high or low?
Yeah. There is a way. I'm not going through it because like I have to skip things for the sake of
Okay.
time. But what happens if you have um, what you could do is um, look at your loss and how it behaves. So if you start seeing what is called overfitting, where the network is really favoring and biased towards your training data sets, and when you try it on a test, a different data set, not the thing that passed through the network, um, you see it performing very poorly. Excuse me. Then this can give you a hint about, oh, the learning rate is high or something, that I'm overfitting. So there's this kind of there's a way to sort of try to study the behavior of your network when you modify the learning rate. Sometimes it's just something that's inherited. So what you do is, for example, you take a network and build on it, and the people who build the network use the learning rate, this 0001, and you just keep using that. And you find out that this is in the ballpark of what it needs to be, and just stay with it. So it's kind of like a conventional wisdom is the learning rate
Mhm.
should be in that range. So yeah, there's a whole field of area studying optimization, right? And then there's part of it is, okay, what's the right learning rate? Of course, Fast AI talks a lot about this learning rate. They try to find an automatic learning rate algorithm that try and gives you a good start. Another thing to worry about is this business of test time performance or validation set. So here it's set to 0.2, and what will happen is when you learn, I'll skip a little bit. This is the loss function I talked about, right? This is the system's performance in terms of how correct or wrong it is, and it's going down. So it starts from 1.1. However, we see here two losses. There's a loss and validation loss. Loss here means training loss. So what you do is you take your images, all of the images, and then what you do is you split them. You split them with things that you will allow the network to see and things that are not allowed to see. This will give you a much better understanding of the performance and accuracy. If you only see all the pictures and never have a test or validation set, then you're only seeing, the network will eventually learn the data set and just perform super amazing. But that's very useless and not general to other cases. So this is kind of a sanity check. It's very important to have a validation test set that will tell you, for examples you have not seen before, what's the output, what's the performance. So here you split by, this kind of a quick rule of thumb, say 20% of your samples for testing, and then 80% are used by the network. The network is gonna see it and learn from it. And 20% are the network uh, validating. So in this case, you can see the validation going down. Once you see this behavior, you are in good shape. Your network is learning on examples it has not seen before. What happens if it overfits or something's wrong? You'll notice that the validation loss will never go down because these are new examples it hasn't seen, and it will never um, learn a function to answer the questions you give it.
Actually, there is a question related to overfitting since you are speaking, you mentioned overfitting. So
Hmm.
how can we avoid overfitting in neural networks?
Okay. So overfitting means that let's say the network state, the parameters are very much optimized for the training. So the examples you already know the answer, the question and the answer, and you overfit. Trying to find a good thing to look at. So let's look at the single case here. Okay. So if I have a network that has 6 million parameters, right? And I show 10,000 images. The optimizer's nature is trying to learn the truth. See this image, this is the output. And if you run it so many times, it always kind of learns to make itself better. For these examples, it can actually reach a point where it's almost memorizing. So all the 6 million parameters are super tuned for the examples you give it. So the model overfits to the training. And that's terrible because you really did not learn anything. You're just learning to mimic the training, the input, not the actual kind of conceptual thing behind it is that, okay, I've seen something dangerous and I'm going to identify it in new images. So I learned what is dangerous, what not. So when overfitting happens, it's just, all right, I've seen this picture. I've already memorized what's the answer. I just, output the answer. And that's a bad way. You're not really learning, you're just memorizing. And this kind of applies to real life is that if you just memorize the textbook, you're sort of if overfit to the textbook and maybe the example. But learning in university or any school is about learning skills that can apply to the real world, to problems outside the textbook. So, yeah, does that answer kind of?
Yes.
Okay.
Actually, the
Um,
question has a second part, if you allow me, Dr.
yeah.
Ibrahim. What hyperparameter cause overfitting the most?
Hmm.
This guy is learning, so I'm really happy about the question.
Yeah, I'm trying to think, like from my experience, what um, I think if you have a high learning rate, you will you will overfit at times. It's really hard to kind of pinpoint and say, this is the cause of overfitting, this one hyperparameter. It's usually a combination of things and the way you train and the way you feed the network the samples. So when you start training and you have, let me try to find a visualization for this loss function.
So is the program done running, or we have to wait also for more time?
I think it takes like 20 minutes. I think it's done.
Mm.
Yeah. Usually it takes 20 minutes. So for this one, it actually, so this is created the data sets, and then I'll talk about these things. And then you can see it learning. The loss is going down. Objective function is met. And when I test it, this is a picture it's never seen before. And it can identify there's a knife here. We can look at another example. I'll generate a completely new image, never seen before. And I'll call predict on it. And here is actually a failure case. Like it kind of identified some of the knife, but not all of it. So, okay, my model needs more training or needs needs a modification. Here, this is the gun. Yeah, found it very nicely. You can actually put multiple things, but I don't have it in the function. But you could imagine you can put multiple dangerous things, and it will identify all of them at the same time. You can see here it's radioactive. So yeah, we built a system that can detect radioactive guns, weapons from this emoji world, uh, small emoji world universe by giving it 10,000 samples. I never told it. I told it what the dangerous things look like, but I never like specifically said, this is a bomb or this is. There's no label. It's a real label. Okay. Sorry. I will go back to the training bit. So yeah. So these are some of the parameters. Another parameters are I call them E and D, or the number of. This is the number of feature maps or weights, convolutional filters for the encoder layers. So if I go back to the architecture view, here you can see sort of a depth, right? So this depth is the number of feature for each encoder. And this picture, they're not equal. You can see here it's like, let's say this is 4, this is 8, and this is 16. And when I actually define the network, sorry, I'm skipping a little bit ahead, but you can see here I'm multiplying by 2, multiplying by 4, this encoder number, and multiplying by 8. Okay. And then for the decoder, it's the same business. I don't know why I picked these numbers. This is just a try and error thing. You can just try different errors and look at the validation and see maybe you can fix this problem, right? So one thing is you can study. Oh, this is very bad that I missed a single instant. It's very clear. My model is not ready for production or real world use. Okay, sorry.
What kind of performance metrics do you use, for example, in your research to judge the quality of the model when it is ready for production?
Yeah, there's several things to consider. Um, if you have a problem that is already established, then you most of the time you're looking at comparing to the metrics that people use. There's a standard metric. So for ImageNet and classifying dogs and cats, there's a standard metric. Everybody's using it, so you can compare your new idea with this performance of past methods. So, for example, in my depth estimation, I have everything is given to me by all the previous papers in terms of okay, this is a table of how the accuracy is for depth estimation. Try to beat that. That's as simple as that. Right? Come up with a network, come up with a training, come up with some trick to become better in terms of accuracy. So accuracy could be the pixel, per pixel, and then you do an average, and then that's it. So average error in depth or average accuracy, how close it is to the thing. In our example here, the this is a totally new fictional problem, but at the same time, I have this kind of validation loss. So this is representative of the error. So let's say if you have 10 teams, there's competitions and stuff for deep learning. So let's say you have 10 teams. I give you the data set. I tell you go crazy, create your own network, and there's a kind of a leaderboard, and it shows maybe this is the best performance. So some other group will try, and then maybe they will get this number. So they're better. So this is how I can find okay, I'm going in the right direction or not. Then you say when do you stop? So maybe 0.2, maybe I can get 0.1 if I keep training or this is sort of a kind of philosophical thing or a higher level thing about okay, I just want to beat the state of the art or win the competition, then okay, I just stop at the first time I do that. I don't have to worry much. If I want to apply it to the real world, there's no kind of easy answer because if you imagine this system of figuring out dangerous things in a security camera, then the policy maker or the decision maker will say, I want a 100% system, which is by nature of these networks, it's almost impossible to be able to identify the whole truth for this complex problem, identifying visually something. Even humans maybe cannot get 100% on this task. So now you kind of play a game of, all right, I can get you up to 90%. Is this enough or not? And it's like, okay, I look at different products and yeah, they're all at 85%. If you get to 90%, that's good. That's where I stop. That's where I decide, okay, that's kind of my goalpost. If I reach 90, then now it becomes the state of the art and everybody wants to beat that 90. So it
Okay.
all has to do with your target in the end. If you want to deploy the system, then you need to have
Okay.
some target, and you try
Uh,
to get towards that target.
I also have here a couple of questions that were asked at the beginning of the webinar, but I asked him to hold on to them. Um, so after a convolutional layer, why do we have more channel than the image before the convolution? So Abdullah, if you
Yeah,
can remind us which slide your question is about.
The slide where where the convolution was, the slide before this one, I think.
here.
Yeah.
Yeah. So let's look at this. This is a single image, right? So let's imagine this is a single feature map, or yeah. It's not called the layer here. It's just a feature map here. So I have a single image, and now I have 16 of these, right? This 16 come from 16 filters. In this case, it's 4 by 4. 4 by 4 is 16. So each one of these images is the filter applied to the entire image. So now I have 16, right? It's more. But actually, what happens is the XY spatial resolution has been cut by half. And that's because of the nature of like we're trying to encode into a space that has a small spatial resolution. So the same image, but you know, depth-wise, channel-wise, it's more things, more information. But spatially, XY, it's smaller and smaller, 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 all the way to becoming actually a single vector. Then you can compute a probability on the class because the classes belongs to this kind of a very discrete subclasses. In the case of the tutorial, we have what is called a dense output. It's not just a single thing. No, it's per pixel, the same size of the input. So that's why we go down, but then we go up. We go up in the opposite way. So we have many uh, many channels, and then we take them to this sort of a deconvolution or the opposite of a convolution, and we have less and less and less and less until we get to one channel. In this case, it's just a binary mask that says, where's the dangerous thing and where's the
Okay.
regular things.
So does that finish the answer to the question?
Oh, yes, yes.
Yeah. So
Okay.
these layer here, you can see 16 channels. Let's see, 5, 5, 5, 6, 1, 2. In any case, it started at 16, and then there's more filters here, and then the output of these is 36 features,
Okay.
but smaller images.
Fine. We have another question from Hashim. Hashim, you will have to tell us which slide the question is related to. What do you mean by input weight? This is a question for you, Dr. Ibrahim. Okay, go ahead, Hashim.
And the slides that I think the previous one for this one. No, yeah, the following one, the next one. No, sorry, the next one.
This
No,
one.
no, I think slide number 14.
This one.
The following one, please.
Okay. This animation.
Yes. So you referred as the numbers that are the weight.
Okay. These numbers at the corner. These are the multiplying factors, the weights that you apply to the corresponding pixel. So this pixel on the top leftmost, let's call it 0, 0 here, it's going to do 3 times 0, which is a 0. Now keep it there. Just keep this new value here. And do it all for the different weights. Then you sum it up, and it will end up being 12. So this is a feature map. It could be the input. It could be something in the middle, like one of these 16 channels. And you apply the convolutions, the filters on the maps, and then you get the output. This is the new feature map now.
Okay.
The output of the convolution.
We have another question from our future expert in deep learning. It seems that he's in a good mood tonight, so he's asking many questions. Muhtadi, go ahead.
Okay, after الصراحة دكتور. Anyway, دكتور إبراهيم,
We cannot
can I
hear you.
can you hear me?
Yes.
Okay, just speak
Okay.
louder. I think.
Okay. So how can I decide the number of layers and the number of nodes in the model?
Okay. So, like I said when I talked about how people come up with networks. So AlexNet, they try to, I think, well, at that time, they try to make a compromise between number of layers and size of image and batches and all kind of things. And let's say they found, some kind of sweet spot that allows the learning to perform well. Later on, people don't start with a random thing. Usually it's kind of like building on top of it. Okay, Alex used 5 layers or filters at that point. Then I'll use 6 and see what happens. Then, maybe I try to put a lot of layers, but my quality is still low. I need to be smart about it. So more efficient architectures would be defined. So it's not just the even though it shows it like this, but in reality, this is not the final kind of output of what the system looks like. It's usually a sort of a network, and there's things called skip connections and residual paths, and much more intricate details about what's going on here. Some kind of efficient multiplication, some layer, and instead of taking one layer at a time, you could take a layer and then add another layer to it from a previous step. So, okay, and then you say the same question stands. All right, how many numbers of layers I need to add? This is a design choice. This is a design question. The way you go about it is look at what's existing. Never reinvent the wheel, and then modify on it and add, remove. Generally, the sort of intuition is that the more layers I add means this network is more complex. A more complicated network with more parameters has more compute or logic, more. It's obviously more compute intensive, so it could capture a complex functions. So if I want a function to read lips, then I need to know language, I need to know lips, I need to know a lot of things. So I need a function with high capacity, many parameters. The analogy here with this imperative coding, I need a program that has millions and millions of lines of code. And then that program will automatically be learned in this deep neural networks to represent my goal. So, all right, how many layers do I need to put? Let me go back to the code. This hyperparameter, I said 32 here. Why 32? Because that's a number that's divided by 2, and some networks like this, some GPUs and computations like this multiples of 2. But I could start with any number, 34 or whatever, and then at some point, maybe if I put it at 64 here, I'm going to be at the disadvantage because parameters take up GPU. So they're going to fight over either having a large batch size, more samples to see at one kind of go at it, one forward pass, but I didn't talk about that, but one iteration of the learning. But I don't have enough memory to see more. Then, I have these two kind of conflicting objectives. Either I encode or put more parameters or see more images of this. at the single step. So then you have to really kind of do a search and maybe look at different papers, different architectures, what they did, and try to experiment up to a point where you see, all right, I found the sweet spot of 32 for encoder, 64 for decoder. So it's very much experimental.
Okay. Dr. Ibrahim, one of the questions that we love to ask our guests is how do they learn? So on one of the slides, you mentioned that you started with that Udacity course. So that was your first experience with deep learning and computer vision. So how much time?
Not computer vision. Computer vision, there's courses
Oh,
and
sorry.
you can take some. Yeah.
Yeah. So I mean deep learning. So how much time did it take you to reach the level at which you are now? And it seems that from the quality of resources that you shared with us, you are doing a lot of learning on your own. So can you tell us about this?
Yeah. So it's ongoing and it's a bit overwhelming, even for me. I've been in this business for long. I have a PhD, but it's very overwhelming because the venue where people present new research, CVPR, would have 1,000 paper, and there's not just physically not enough time to to go through 1,000 papers and try to learn something new. So the way I learned was my supervisor recommended this course based on some recommendation. This course took around 4 weeks, but 4 weeks of completely just dedicating to this course. Since I was a postdoc, I had the luxury of not doing anything, just taking the course. So I finished the course in 1 month. It's designed for 4 months, but if you do it full time, you can do it very quickly. Then our group, including our supervisor, looked at the Fast AI course. So it's a series of 7 hours or maybe 12 hours of lectures, and we had to weekly find the most relevant lectures and look at them. So at this point, I did some projects, I did some learning. Now I'm ready, let's say, to try to experiment myself. So what I did is I go to Papers with Code or find some GitHub repository, and then I literally stare at the code and look at so let's say this is the network architecture. So I look at it, and I look at multiple things, multiple papers, and look at the paper and try to see why did they pick the kernel size 3 here? Why did they use same padding? What are the first when they initialize the weights? What initializer they used? And then you kind of start to be an insider. Now okay, this is what people use, and this is what generally works, and you you accumulate this knowledge of what works and what doesn't work. Then you can sort of skip a lot by going and seeing what's the state of the art. So you go see the state of the art. The state of the art, let's say, is using for their optimizer, they're using, optimizer. So let's say they're using optimizer Atom. Okay, I'll stick with Atom. And that's what I've been using. A lot of people are using Atom. I notice, okay, every time I see a paper, I'll check, okay, which optimizer they're using, what is the learning rate they have. And then you kind of, in your mind, you have now kind of carved out the surest path of how to get into, how to come up with a model that's good. Then, once you kind of moved on to more advanced, like you've passed this point of creating a cat dog classifier, you're more into deeper challenging problems. Then really what kind of is super valuable is following the trends of scientists on Twitter and maybe like something on Reddit. And internally, our group, we have a Slack channel that is for group discussion, and we have one channel that has hot stuff. It's the super recent things to look into. And every time we discuss it, okay, what's the idea in here in this paper? Then you kind of try it out. Most of the time, it never works. And maybe sometimes it works, and then you say, all right, yeah, I discovered that they did this trick in the input. They did some processing on the input that resulted in a better model. And it's a lot of this experimental. It's kind of like a natural science and chemistry or whatever, where you have a grid of experiments you want to try. And then this is the same thing here. You have a grid of hyperparameters and architectures, and then you try different ones.
Of course, this is on top of your daily job and your other commitments.
Yes.
Um,
But this is one thing that that you get taught by your supervisor or your teacher. Good time management. Something you don't you don't get born with it. You kind of have to face it when you have a lot of jobs. So you kind of estimate, if I sit down on deep learning things, then I will take X amount of hours, and then I will do that on Saturday, and then on Sunday I will work on the other task, and so on. So having a good time management skill is also very valuable for this, because you're working with things that learn on the scale of days, and you have limited hardware. Even with KAUST budget or facilities, you still are sharing the resources, so you can have a limited hardware. So you're kind of hoping to do something meaningful, like a meaningful experiment, to kind of only perform the experiments that are hopefully going to get you something new, get you a paper, get you some interesting new results. So there's kind of a lesson here that to to time manage yourself.
okay. So I think we have to wrap it up. Although we have been
I want
really
to show
enjoying.
just
Yeah. Go
some
ahead.
things here. All right, very quickly, I'll kind of run over it very quickly. You guys can look at it at your own. So the inputs, again, I'm reading the data sets, right? They're in memory now. I have the y's and the x and the y's, the answers and the questions. This is just to divide and make them from 0 to 1 representation. And this output is not the output of the algorithm. This is the output of my experiment. So one kind of thing to try to learn is to always output runs, like create a folder for each experiment. This way you don't get distracted by what happened here. And then the name of the file is the parameters, the hyperparameters. So then you'll have like 50 experiments later on when you accumulate. All right. So we have an output of the experiment, and we have some kind of helper functions to take the model.predict and then do some kind of just reshaping of the shapes. There's something about saving PNGs. Always have samples, intermediate samples. So in this case, when the model first learns, it will have poor quality, poor accuracy, and then later on it has very nice accuracy. See here, this is the first step, the very, very first step. This is the output. It's terrible. And you can see the knife, very obvious. So after running through it 30 times, this is the accuracy of the model. Now I can visually see and impact that, oh yeah, the model is learning. Another big, very important thing with the hyperparameters is the loss function. Loss function is describing how do I judge my performance per training step. So in this case, it's going to be, it's going to be, I know the ground truth, right? Let's assume this is ground truth and this is me. So I can subtract the pixel values and find, okay, I'm correct here and wrong there. So for binary or for classification, you have different loss functions. These are kind of standard, and then, but they play a big, big role of how good you're learning. So you have this binary cross entropy loss. And what you do is you take your true y, your true answer, and the predicted y, and then you compute this difference thing. This is a two loss. There's two things, two statistics on the inputs here, and that's your loss. Your loss could be a single value that's the average, or the mean, or the average of the entire loss here. Okay, so this is loss function. This is very important. It's a very important concept to learn about. So, but I have to skip it and then just go right into how I define a network. I'm using Keras here, and then Keras layers, convolution layers, and optimizers. I'm sorry, I'm not using SGD. Should be not included. And then this is how you define a network. So you say an input layer takes input images, this shape. You do convolution, and then this is the number of filters. And every time I'm taking the same thing, I could call it different things, but this is a kind of an easy way to look at it. So I take the input features, start off as just an image with 3 channels, and then it goes all the way to a small image with a deep or channels, number of channels. That's the end of my encoder, and I go back the other way, which is the decoder. So this is it's not doing a deconvolution; it's doing a convolution followed by upsampling. So but it's a way to do the inverse. I grow spatially, and then I end up with a single channel. That's the mask channel with the size of the image itself. Okay, that's it. I defined my network. This is my network. And if I define the network and kind of list it out, there's a function to display it in the Keras. You can see here the number of parameters. So the input does nothing, 0 parameters. And then the next layer is just a couple of 32 filters, so it's 896 filters. And you see them kind of increasing and then decreasing. And then there's a summary here. So this model you've seen here takes around 15 minutes to train and gets you this performance, is made up of 25 million numbers. 25 million numbers, and that's the way they are connected. It's described this way. And that's my model. I think it will cost, compressed, it will cost probably around 40 megabytes. So a 40 megabyte is all I need, well, with the CPU, obviously, or a GPU, to be able to find dangerous things from this image. So just I'll go over this Atom. That's the optimizer I'm using here. It's usually very good, and the rate is 0001. This seems to be a magical number. It works a lot of time. You create the model, and then this is just some kind of logging and debugging things. And then what you do is you just call model.fit. For Keras, it's just a single line to tell it these are the questions and answers, and do it for epoch, 30 epochs. So 30 times go over the entire data set, and then it will automatically does the rest for you, this kind of loss and kind of timing and everything like that. And then once it's done, I can call predict, and I give it some scene, some generated scene, and this is the output.
Okay.
That's it.
I have one last question, if you don't mind. It seems that many of the students, they want to get into the field of computer vision and deep learning. So the question says, should I take a course on digital image processing to prepare myself for concept like convolution, or it's enough just to skip this step in my learning journey?
It depends on your target. If you're an engineer or practical, or like you're going to be applying and kind of hacking things around, then you could just read about them. Just read a Wikipedia, watch some videos like the videos I showed, and then just use them as tools. Now, this will still give you power to build things, but if you want to think about speed and optimization and how to increase and decrease the number of parameters and what's the latest trends, because the convolution layers are getting more complicated. They have different ways of doing it. So you have to kind of be on top of things and sometimes have to know the details of, okay, how did they implement this or that? I think most courses, they teach you the math, the theory behind it, and then in reality, when you practice, you never bother with these low level, let's call it low level things to consider. So I think for digital images processing, or let's call it classical kind of computer vision, it's helpful, but it shouldn't take too long. Like you can do a very quick overview of, okay, how to open an image, how to apply a blurring on the image, and that's about it. Because what ends up happening is you are not defining the functions. You are doing this end to end. So you're giving a structure of your model, you're giving inputs, you're giving outputs, you're giving a loss, something, a function, an objective that the learning process is trying to optimize, and you just let it go. Like you let it do its thing, and it will come back with these convolutions. And you never have to look at the single convolutions. It's impossible to look at them. Like I said, this is it's 4 million, or just sorry, 25 million parameters. Nobody ever bothers to look into it in the end. Or so you need to have some kind of knowledge about what's going on behind the scenes for sake of efficiency and for maybe sake of how these would scale, or maybe what's the latest convolutional layers that people are using.
Okay.
Otherwise,
Can you go to slide 43? I think it will give us a good closure for the webinar. Slide 43.
43. Okay. Yeah.
Yeah. Do you want to
This
say a
is kind
few
of
words?
yeah. This is the end. Yeah. So I'll just go over it very, very quickly. All right. So how do you apply deep learning? I had this class for general audience. This slides for general audience. How do you apply to your work? So whatever you are, you're an engineer, you're working with stock market, financials. You need to keep up with the latest trends, because if you think you saw a method and you want to replicate it, usually it's already old and considered to be obsolete or useless. So always try to see what's out there and how recent it is, and people comparing and contrasting. Big data can be a deal breaker. If you don't have enough big data, what is big? It's not a easy answer, because it depends on your objective. You want to be 100%, then you need to have billions of images, but you cannot get billions of images. So you get what you can collect in terms of money or time or effort. So if you have 10 samples, then it's very, very tricky to try to get high quality or high accurate models. So big data can be a deal breaker. If you don't have the right data, or you don't have a way to deal with the limitation of the data, then you might not go anywhere. One way to do it is maybe synthesize your own. This is what I did with this emoji world. I synthesized my own because it's just it's a cool way of building it fully in one file, and I can generate infinites of it. You need to worry about the resource management. So if this is you learned this the hard way. If I give you 10 GPUs or 10 servers, each has 8 GPUs, and I give you all, I'll tell you start away, and you think, I have enough compute resources, then maybe, I will just do a grid search. So find every single parameter and do a matrix of the different hyperparameters, and then I will get a good output. Usually that never works. What you end up with is a lot of mediocre models and then maybe a good one. But that's a maybe. So you need to be mindful of your resources. Okay, how many GPUs I have? Maybe I need to start with something that's already existing and then start from there. Usually that's always the winning strategy. You download a network with weights already for some task, and then you do a transfer learning. And you need to be aware of the limitations of deep neural networks. There's always a big challenge of generalization. So how really its performance is in the real world. So I built my lab, clean, nice data, everything's great. And then I go out with my camera and cell phone and everything's broken because it really didn't generalize well at the real world. Type of intelligence problem. you cannot solve all problems. I have a comic at the last slide regarding this. You need to be realistic about your goals and what these networks are capable of at this level, at this time. Maybe in the future they can be better, but right now maybe they cannot solve this specific problem. And you need to be careful about actually people can fool networks. So on the right here, you can see a 3D turtle that people printed with color, 3D printed object with color, that every angle you put a camera on, it will say that this turtle is a rifle. So there's kind of an inherent limitation in these networks that you can numerically trick them into seeing the wrong thing. They don't have, there's a robustness issue to worry about. AI is a growing field, and actually commercially, if you start an AI startup, you have a kind of smart idea, you have data, you have a good model, then there's actually millions and billions of funding out there for you around the world. And with that, I will end. This is the comic I was talking about. You have someone who people come up with a computer person, and I have algorithms to solve it, and then 6 months later, he realizes, oh, it's a hard problem.
Hard in the computer science sense?
No, I think like you can imagine maybe these are biology people. They want to invent a new drug, and this kind of a bit hubris attitude that I have machine learning, I can solve anything, and then you realize this problem is complicated for a human to solve, not to mention how to encode it for machines.
Okay. Everybody is asking about the slides, and I don't know. I do know why, because of the quality of information and the resources that we have seen today.
I'm glad you guys like it.
I have really been trying to move into this field of computer vision and deep learning for quite some time now. And I think with the resources that you shared with us, that will make my switch smoother and easier, inshallah.
I'm
Shabab,
glad. More allies that study computer vision, the better for us, for the
yeah,
field.
yeah. And also for the students, I would like to say that, well, the bar is high. And for those who have their projects in computer vision and deep learning, you're going to sit with Dr. Ibrahim, and you need to prepare very well. Because as you can tell from his presentation, uh, he knows a lot of things about deep learning. So you will be challenged throughout your project. Okay, so you need
But
to
don't be
prepare very well.
discouraged. Don't be discouraged, bro. It's
Okay.
you're gonna do well. Just put effort, and it will pay out.
Inshallah. So, Dr. Ibrahim, on behalf of the chairman of the department, faculty, and all the students, I want really to thank you for such an interesting and useful session. And also, I want to thank you again for having two of our students in your doing their summer training in your company, and for your help and assistance with our training program. And we look forward to seeing you in the future, inshallah.
Inshallah, thank you. It's an honor for me to be invited, and I really hope that the talk today was fruitful and exciting enough for people to go into this field.
Okay.
And thank you all for listening and for your time. I think we took a lot of time.
No, that's fine. Okay. Thank you, Dr. إبراهيم, وتمسوا على خير جميعا. السلام عليكم.
عليكم السلام. شكرا جميعا. مع السلامة.